So yes, let's start today with an example of compositional verification and how we can use composition verification with CoCoSim. So we are in the repository of CoCoSim in GitHub. I will use an example that I put in the documentation. So if you go to the doc folder and then the examples, here is a very simple example that I will use today for demonstration. So we have here a system called ES, which is the whole green um, box, and the system has an input. That input is linked to a component called A, and then the output of A is connected to two inputs, one for B and one for C. C has two inputs, one coming from A and one coming from B. And then the C output is the same as the output of the system. So in this example, it's like Simulink. So this is the whole system ES, and A, B, C are subsystems. And we have contract attached to each level. So we have the root level, which is the top level system that has inside A and B and C. It has the requirement says ES, which is the assumptions of the system S, assumption the input is less than 10. So we are, sorry about that, I clicked on the assumption of the input should be less than 10. So that's the environment. So we have a precondition on the system. The input is always less than 10. And the output of the whole system, which is the output of C, should be less than 50. So it's a very simple example. Input should be less than 10, and at the end, the output should be less than 50. And then we have a specification for each component, A and B and C. So the assumptions of A, that the input should be less than 20, and the output less than 2 multiply inputs, and so on. Each component has a contract describing what the component should do. And in this case, we want to know if the components or the contracts of the component satisfy the top level contract. So that's compositional verification, is that can we prove that the guarantees of the system are satisfied for the given assumptions of the system. So which means that ES implies BS is GS guarantees for the given contracts of A and B and C without seeing the implementation. Like we don't care about the implementation of A and B and C, we just have an abstraction, and that abstraction is the contract associated to it. So we have a contract for A and a contract for B and contract C. So can we prove that all these three prove the top level system? Are you following me? Yeah. So the first thing we need to ask ourselves, on the left there is example to prove. What we need to prove? So first of all, that the assumptions of the whole system needs to prove the assumptions on the inputs connected to. So this assumption on the input that less than 10, does it respect? So A has an assumption that the input is less than 20. So the assumptions of the system respects that. So imagine that the assumption of A is input less than 5. That's not good because A is assuming that the input is less than 5. But the system is assuming that the input is less than 10, which means that the input can be 9. Okay? And in this case, if the input can be 9, that does not respect your A component. And CoCoSim will tell you that, hey, your assumptions are not respected. The A assumption, the component A assumption, is not respected. Okay? Well, so in order to prove that the whole system is behaving correctly, we need to first prove the first line of the proof. So these lines, I'm talking about, talking about the lines on the green. The first line says the assumptions of the system should imply the assumptions of A. Why A? Because it's the one connected to directly. Not so the input of system is the same input of A. In this case, it's correct. So the input is less than 10 implies that the input is less than 20, less than 30, or less than a million. So it's correct. The first line is correct. And again, we need to prove that the assumptions of all other components are respected. So what about B and what about C? So whatever a component you have, you need to make sure first that your preconditions, your assumptions, I call them preconditions and they are the same as assumptions, are respected before proving the guarantees. Okay? Because the guarantees are for that specific assumption. So in this case, B, what is the assumption of B? That the input is less than 20. How we can prove that the input is less than 20? It's the assumptions of the input, the system, ES, with the guarantee of A, whatever the output of A is guaranteed, should implies my assumptions of B. You understand? So that's what CoCoSim or Kind2, we are using Kind2 to do this reasoning, is trying to prove. Does my guarantees of A, so does the guarantees of the component A satisfy the assumptions of B? Okay, so for the given input of the system and for the given guarantees of A, does it respect the input of B? Do you agree?
Yeah.
So in this case, is it true or not? So the input is less than 10.
Okay.
And the output is less than 2 multiply input, which means that the output is less than 20 because 2 multiply input and the input is maximum 10. You agree? It's just math. Input less than 10, 2 multiply input is less than 20. So the output should be less than 20. And the output is the same as the input of B. So the input is respecting 20. And because of we use the assumptions of the system, not the assumptions of A, because the assumptions of the system that are the true assumptions, that are the environment assumption. So B, this one input less than 20, if you use it, it's not enough because if the input is less than 20, 2 multiply input is less than 40. But we are sure that the input is less than 10, not 20, because we are using the assumptions of the system. That's why the second line says assumptions of the system, because they are the one. So it's like the assumptions of A can be more general, but at least they can be more weaker, but the system are stronger, because the system assumptions implies the component. So, because of the first line, in fact. So the second line respects that. The input is less than 10, which is assumption ES, and the guarantees of A is that the output is less than 2 multiply input, which means that the input of B is less than 20. And the same thing for C. The first input is less than 20, but we don't use it in the assumptions. We don't need them in C. So, and then now we need to prove the assumption of C, but the C has no assumptions, so we don't need to prove anything. It's just like for C in this example telling you, hey, I'm the big thing, I'm minus infinity plus infinity. You don't need to worry about me, okay? But anyway, we put it in the third line in the proof. So these lines are general, like AS with the guarantees of A and the guarantees of B should imply the assumptions of C. It makes sense. It's very simple. You follow? So whatever C is connected to, that component guarantees should help prove the assumptions. It's like you divide the proof. That's why compositional verification is very useful. Because it's like, hey, my task is done by these 3 people. And I need to prove the big property. The big picture is that I need to prove that the output is less than 50. But how I can do that? I can try to divide the logic in the 3 components. So for example, if A is doing multiplication by 2, then I should prove that output is less than 2 inputs. That could be like an implementation, a very simple implementation that can respect this contract. It just A is doing multiplication of 2 of the inputs, and it will respect this contract. You agree? Because if you do just 2 multiply inputs, then the output is equal to 2 multiply input. It should be strict, sorry about that. Sorry. So the output should be less than 2 inputs. So for example, if you multiply the input by 1.8 or 1.9, that's good. You are always less than 2 multiply input. Okay? In this case, I don't know if we want to use integers or doubles, but it's the same idea. For example, if you want to use integers, you can use a simple implementation of a could be 2 multiply input minus 1, the input minus 1, and then you multiply it by 2. It's always less than 2 multiply input, just as simple mathematical, making sure that there is no overflow when you are in the bottom. If you are just using math, then that's simple. When you put the machine integers in the picture, you need to make sure that things there's no overflow. But anyway, I'm talking here mathematically. So the big picture is like, here is the composition why it's useful, because you can decompose your property on all components. What do I need to prove in A individually, and in B individually, and in C individually, that can help me improve my top level requirement? That's what we need as engineers to do, is come up with requirements. When I say requirements, is properties, is come up with the properties with guarantees on each individual component that can just use them to prove the top level one. You don't need to do this by hand. You just come up with as much as you know about A, as much as you know about B, as much as you know about C, and then just hopefully can prove things for you. You don't need. If we do it by hand, then there's no need for CoCoSim. You understand? And that's where compositional verification is. So you understand how it works? It's just like you decompose your property on different things.
Right.
So in Simulink, we need to have 4 contracts. 1 for the system, 1 for A, 1 for B, 1 for C. Okay. So now when you run CoCoSim, what it's doing is proving all contracts. So first it tries to prove that the contract of A is valid against the implementation of A. So as A as a component, does A respects the contract, the implementation? So those are like the root of the tree.
Okay.
So A, there is nothing inside it. For example, there is no contracts inside it. It may be a very big subsystem with a lot of other subsystems, but we didn't specify it any further other things. Like we stopped at A.
Right.
Okay? But you can do this reasoning in different levels. Like let's say A, you also decompose the property of A into A1, A2, A3. Right. Understand?
Yeah.
And you can do it as much as you want until you reach the level. If you are able to do it, if you are able to help the solver with that, that could be useful. But are you able to come up with properties? That's the question. Okay. So that's the point. Is like I need first to prove that my contract of A is valid against the implementation of A, and then I go, is B valid against the implementation of B, and the contract of C is against them. And now to prove the system S, I need to make sure, oh, now I can use just the contracts. I don't need to use the implementation of A or B or C. I can use just their contracts. Are they strong enough? Are they enough to prove the system property or the parent's property? You can have different parents. So you can have A has children with different contracts. So are the children contracts verify A, and then A with B, C. So we see what I mean. So in kind 2 is doing many verification, doing 4 verification. First A against implementation, B against implementation, C against implementation, and trying to use A, B, C to prove the system. So why it's useful? It's useful is like if A, let's say, A is very hard to prove. Okay. It's a lot of lookup tables, I don't know, nonlinear arithmetics. It's very complicated. Maybe it's the flight software thing. But B and C are simple. Okay? So I can tell CoCoSim, hey, I will help you with A. I will not provide you with contracts of B and C, but let me help you. I will give you abstraction of A. Okay. So you don't need to give you don't need to give the contract for everyone here. You may give it just for A. You understand? And in that case, what does this mean for kind 2 to prove the system level property? It means that kind 2 will use the implementation of B and the implementation of C plus the contracts of A. You understand? So kind 2 it can use as much information as you give it. So if you give a contract for A and only, it will use the contract first. and if the contracts is enough to prove things, then it tells you, yeah, you should be happy. We can prove things. Okay, we can prove the system level. But if it's not enough, then it will use the implementation of A. It's like, hey, your contracts is an abstraction. It's not precise enough. Always contracts are not precise enough. It's like if the implementation of A, as we said, is the input multiply 1.8, we didn't tell him output is equal input multiply 1. We just tell him it's less than 2 multiply input. You understand?
Yeah.
It's an abstraction. We hide things for him. But is that enough to prove things? That's the question. In this case, it's enough because we are proving some inequality. Understand? So what Kind2 is doing is like, hey, I tried to use your contracts only and I couldn't. I found a counterexample because the abstraction is more, it's not precise. I found a counterexample. Let's now try with implementation. So Kind2 is trying different combinations. Let's try contracts first. If it's fine, we can prove things. We stop there because we proved it. We don't need to go to implementation. We avoid to go to implementation because implementation, that's why we add the composition verification, to hide the complexity of the system. So when Kind2, the question is, when Kind2 goes to the implementation, only under one condition, is that the contracts of A should be valid against A. So first of all, as we said, it's a bottom-top analysis. We start from the bottom. We start proving contracts A against implementation, and B against implementation, and C against implementation. And then we go to the system. If A is true, it's like the contracts of A is valid. And then to prove the system, we will use the contracts A and B and C. And let's say these contracts are weak enough, okay? They cannot prove things. Then I will try a different combination. I will try abstracting A and B and not C, or B and not C and not A. I will try different combination. This is automatically done by Kind2. And I will try different combination. But under one condition, that you only use the implementation if that contract is true. Like you will not use implementation of A if the contract of A was not proven valid. You understand? So fix yourself first. That's the philosophy. Fix your bottom things. You need to make sure first that the contracts of A is correct. Maybe that's why you have a problem in the higher level. You need to fix the children before asking to prove the parents. So if the contract of A is not valid, go fix it first. Then if you fix it and you give us a valid contract of A, next time we will try to use the implementation in case that the contracts are not strong enough. You understand? And why compositional verification is nice? Well, let's say A implementation is not good. The A contract is not proven valid, but Kind2 is trying to use it to prove things. And then you found out, oh, he could prove Kind2 can prove that the system contracts is true using only abstraction of A and B and C. But A is not valid. What does it mean? That if you go fix A, then you fix the whole system. And by fixing A, I mean that you didn't break that contract that was, you see what I mean? It's like maybe you added another property where you fix a small thing that didn't, you can still be a stronger version of your, you see what I mean? So that's the philosophy. The philosophy is like decompose your property into different properties in your system. Okay, we can give an example. So ABC, that's why it's called, this model is called ABC.
Okay.
Yeah, it's the same example.
Okay.
But in Simony. Here ABC1, I just copied the system. That's the S. That's the AS, and that's the whole system. And inside there is A, B, C.
Okay.
You see, and S has a requirement. It says assume input less than 10. Let's make sure it's the less than 10. You don't need that. And guarantee that the output is less than the output is less than 50, and we don't need the input, I think. So I will remove the input. The output is less than 50. Okay, that's what it says in these two lines.
Okay.
I'm talking about ES and BGS.
Okay.
So we implemented this. We implemented input less than 10 and output is less than 20. Okay. Now we should go bottom. Now to the second level, and we need to specify the contracts of A and B and C. Okay. Let's specify a contract for A. What should we say about A? We should say that the input is less than 20, and we should guarantee that the output is less than 2 input. A way to do it is just you can attach a contract.
Okay.
So I showed you in the previous videos how to attach a contract. You just go to the library, but there's another way. You just click right, and you can tell CoCoSim, hey, attach a contract to this one. And that will be done automatically.
Okay.
But in a different way. What does it do? It just like try to put A inside another system called A abstracted. You see? It's like I created another system, A, is the same A of before, and I attached a contract, and I put it inside. Why? It's like hiding the contract. You don't want the contract make your model not readable.
Right.
It's just like to keep the same design.
Okay.
Okay. Omar, I'm doing a video. Okay. So here is an implementation of A, and there's a contract attached to it. We can do the same thing. We can attach B.
Okay.
And we can do the same thing for C. We still need to specify the contract, and this is just helping you come. It's very nice, and it keeps the model the same design.
Right.
It doesn't give you. It's more readable. Yeah, it's more readable. So here the contracts. I already have the contracts done in another file. I will just go and copy it.
Okay.
Okay. What this for A should say that the input is less than 20. Let me make sure it's correct. And should say that the output is less than 2 multiply input. Okay? So now I finish with A. I should move to B and move to C. Okay? So we can just close this one. I just wanted to show you how I did this. And open the one that I already did everything for. Okay?
Okay.
So this one is fine. B is fine. Input less than 20, output less than input plus 15. Just making sure that that's what is here. And that's what is here. Perfect. And that output is equal to the sum of inputs. That's what it says here. So we finished. There is no assumption on this one.
Okay.
So we specified. And here are our implementation of something. I come up with an implementation. Like output equal to input plus input. That's the same thing that the contract is talking. It's saying the output is equal to the sum of inputs. So that's a correct implementation.
Okay.
You understand? So the contract is just telling the same thing as the implementation. So it's like always the contract is an abstraction. It could be the same as the implementation, which is in this case the output is equal to input plus 1, input plus 2. Just you repeat the implementation because it's just a silly example. But always it's an abstraction. It's even the same implementation or something that is more less precise. But you see what I mean?
Okay.
So for B, that output is an input plus 15. So if you add 14 to the input, you should respect that the output is always less than input plus 15. Because input plus 14 is less than input plus 15.
Right.
You understand?
Yeah.
So I'm just coming up with the implementations that respects this. So here is that the output is less than 2 multiply input. If we are using real, we can do just 1.8 multiply input. But I think in this example, I'm using integers. So what I do input minus 1 multiply 2. So this should be always less than 2 multiply input. Because input minus 1 is always less than input.
Right.
And if you multiply a positive integer, it doesn't switch your operator.
Right.
Okay? So
hello. Bỏ lại đây có gì đâu. Đã làm chút, làm bỏ lại chút xong không có sao hết. Yeah. Ok. Nó có gì đâu, làm chút lại. Ok. Ok. Okay, sorry about that.
Let's continue. The S spec is the same. Okay. So now we have implementation of ABC example. So if we try to prove things, what we will expect? We expect everything to be correct. We have a correct implementation of A. Did you saw it? Mathematically is correct. B is correct, and C is doing the same thing as the contract. Just the output equal to the sum of inputs. Okay. So we should expect something. Everything is valid. A valid, B valid, C valid, and the system is valid because we just copied the same picture. So we just did the same thing here, and we give a correct implementation of A and B and C.
Right.
So now if we run CoCoSim, let's wait while it's running. I assume that we need to get something correct for all of them, okay? Unless we've missed something about integer overflow. But we don't have here. Yeah, we have input minus 1, for example. If you have the input minus 1, you may, if you have like int 8 and you have minus 128, if you do minus 1, you go back to 1. You go back to 127, okay? Unless you do saturate on integer overflow. If you saturate, you keep the same, minus 128. You agree?
Okay. Success.
No, not success. That's just telling you that your model is compatible with. Oh, we have a counterexample. Oh, it's the same my counterexample, minus 128. I told you.
Okay.
I am kind to.
Yeah, you're quicker than kind to.
I told you that machine types integers are tricky. So C and B are correct, and as I expected, only A that is not correct. Why? Because we have input minus 1, and since it's machine type integers, it will overflow in C. But the S system is correct. So it means that if we use the abstraction of C and B and A, then we can prove that the system S is correct. So that's what table is telling you. This is like, yeah, we use abstraction. Okay. Why the A is not correct is the same counterexample, that minus 128, I assume. If it doesn't work, you can go to the property. So you say only A is correct. So if you can tell him generate the HTML table for this counterexample, and you see the output is minus 128. Oh yeah. So the counterexample is nice. So it says here is minus 64. If you do minus 1, it's minus 65. And if you multiply by 2, it's 65 multiplied by 2 is 130. Okay, minus 130. But since you are in integer machine type integers, we will saturate on minus 128. But minus 128 is equal to 2 multiply input, and we ask for the contract to be less strict, less than 2 multiply input. So it's a very nice kind to, you see, it can find very good counterexample quickly. So to fix this, and we just need to there are two like, let's first to make sure this was saturate on integer overflow. So you see it was from the counter example I can tell.
Right.
But and also I write it here to make sure that the user pay attention to that. Because if we change this to something else, it will be different results.
Okay.
We will go to the positive.
Right.
Like minus 130 is not in int 8 will be something positive. You understand?
Okay.
So then to fix this we have two options. We can tell, hey CoCoSim, please consider integers as mathematical integers. You remember this?
Yeah, right.
This is abstract integer machine type by z, by natural numbers. Okay? If we do this, everything will be considered as integers, mathematical integers. You see now it's active. So let's now save this one and try to see if we can prove things. It's nice because you can learn how things work.
Yeah.
So that's why I remember in the last video we talked about the importance of the preference menu, the importance of what you abstract. You know, if you use integer machine type integers versus not, if you use some type of abstraction. Now we can see that everything is valid because we use mathematical integers. C valid, B valid, A valid, and everything is valid. So let's now do something. Let's make things weak enough. I want to make things weaker to tell, hey, some of them are weaker to say, if we weaken some contracts, it cannot prove that the output is less than 50. So how we can do that? So here it says the output is equal to the sum of inputs. We don't have anything to weaker about. And then if the input is plus 15, and if you do inputs plus 15 plus 10, it gives you less than 50. Okay, so the output here is less than 2 input, which is less than 20, so it could be like 19, and here is the input plus 15, which is 20 is plus 15, 35. So 20, 55. Yeah, let's do something like input plus 10 or output. If we do input plus 10, then input plus 10, 20, 30. Let me try. I will tell him 10, and we need to change B to be respectful, so to be 9 here. Okay, I'm just trying to see if we can weaken up these properties, and I'm trying to find the case where these contracts cannot prove the top level one, because this we can just do it by hand and it proves this. Okay. But we want to, hey, this is not enough to prove things, and I will show you why, because in the reports kind of should tell me, yeah, I couldn't prove things with the abstraction of B, but I could prove things with the implementation of B, for example, or something like this. Oh, sorry, this will not change anything because we just changed things. We shouldn't pick 10, we should pick something bigger. Yeah, sorry about that. You understand, because we are looking for less than 50. Oh, perfect. So if we do B, tell him, hey, B output is less than 2 multiply plus like 30.
Okay.
So a big number, or plus 50. Now it's not good for him because he says, oh, plus 50, and they want to prove the final output is than 20.
Right.
Yeah, but this is correct. This contract is correct against B. The implementation we had before, it respects that. So B implementation is respecting B spec. You understand?
Yeah.
Because we just make a very big number, 50, plus 50. But what's happening is that now the contract of spec, B spec, will not be enough to prove the top level one. You understand now?
Yeah.
So if we ask Kainto to prove things, he will give us a very nice table that says, hey, if you use the abstraction of B, A, B, C, then your contract is not valid. But if you use the contract of A and the implementation of B and the contract of C, then you have it valid. Yeah, I will show you once it's... I like this example because it shows how you can use compositional verification, and at the same time it's very fast. You can run it and you can get the results very fast. We don't need to wait for a crazy amount of time. Like things can be proven in less than seconds. You see now, we have a problem here in the display, but you don't care. Like you see, the column is down twice, abstract C, but you have the same values, so it's not a problem. Just displaying, and this is the code of Iowa. I cannot change it. So here what she's saying here, that's the C against implementation is correct. B against implementation is correct. A is, that's what I was explaining to you before. A against implementation is correct. Let's now see the system, the top level system. So it says if we abstract C and abstract B and abstract A, just ignore these two columns, then you have a counterexample. Why? Because we are expecting this, because the abstraction of B is not good. The abstraction of B is saying that the output is this, the input plus 50. So what will be the counterexample is anything that respects that, because it's not using the implementation, it's using anything that can respect this contract. So for example, input plus 49 respects that. So if we go see the counterexample, I will show you later. And then it tells you, hey, if you use abstraction of B and C but not A, you use implementation of A, you still have a counterexample. And I expect that because we didn't touch A. The A is not the problem, it's B. The B, we shouldn't use the B contract. And now it tells you in the third row that C abstracted but not B and not A is proven to be valid. In fact, if you keep A abstracted, you can still have it valid. But Kainto is using different versions, different combinations, and stopping once there's a combination that is good. Understand? But it will not try all different combinations. Like one is missing here, or more than one because C implemented. But you understand the third row. It's just saying the contracts of C, the abstraction of C, plus the implementation of B. This means that we didn't use abstraction, and that we didn't use the abstraction of A. We used the implementation. That can prove that your system is correct. And what this means? This means that, hey guys, go fix your B and go fix your A, and then your system is good. Or you go fix your contracts of A or make it stronger. You understand? Or you don't need to do anything because Kainto is able to prove things using implementation. So you don't need to do anything. If you have someone of these people are wrong, are not valid, then you should go fix it. But since they are valid and they are respecting the contracts are met by the implementations, and you could prove things using implementation combined with abstractions, you are fine. You should stop. Yeah. You understand?
Okay.
So the verification results here in the counterexample, we have two counterexamples. In the case you abstract everything, and in the case you abstract only you get implementation. But both counterexample will be the same because the problem is in the abstraction of B. Okay, if you see the counterexample, it doesn't work in this MATLAB 2020. I don't know why. Here it tells you only valid because there is one case that is valid. So here I will tell Kainto, hey, please use this abstraction of C, abstraction of B and abstraction of A. In this case, so in this context menu, you can tell CoCoSim, show me the colors or the counterexample for this specific scenario, where C is abstracted, B abstracted, and A abstracted. The same thing you have in the HTML report. You have 3 scenarios where everything is abstracted, where 2 are abstracted, where 1 abstracted. Okay? And this one, that is valid. If we click in this one, it will be green. You see? But if we click in the one of the other 2, this is for the system S. The others they don't have any other options because they don't have other contracts beneath them. Okay? But if we use, for example, this one, and we ask him to show us the counterexample, it will give us for B, the B abstracted local 65. And what is 65 is the input, which is the output of A, 16. 16 plus 50 is 66. And you want anything that is less than 66, which is 65. And you see the problem which comes from is the abstraction. So here, the values you see here, they are coming from abstraction, not from the implementation. You remember the implementation is plus 14.
Right.
The input is 16 plus 14 is not 65.
Right.
But we don't care about the implementation. We are using only the abstraction. That's why we are using compositional verification.
Right.
And that's dangerous because you need to understand, hey, Kainto is not using implementation, he's using abstraction. That's why if some people say, oh, that cannot be. You have 16 and plus 14. How so you have 65 here? No, your contract is not valid. Your contract is saying anything less than input plus 50.
Right.
Okay, you understand? Now, yeah, I think you get the idea. Like, once you fix the contract, then everything should go back to normal. Everything valid. Okay. Yeah. So the contract is the problem, not the. So what does it mean? That it means that we use abstraction of these people to prove the top level. Perfect.
All right.
Good.
Good.
Do you have other questions?
Not now, but you're taping this, right?
Yeah. Perfect. Let's end it.